Hello, my name is Chris Leon, and today I'll talk about the residual mean field model and a possible universal limit for valence PDFs. So the residual mean field model was developed by my advisor and I to better analyze valence quarks inside the nucleon. So the nucleon is a complex object. It can be expanded in a Fock expansion. No one's been able to solve the issue with QCD, but we take a phenomenological approach where we divide the nucleon into valence and residual system. So the valence system consists of 3 valence quarks, and we use the fact that even though quark number is not conserved, flavor is, so we treat these quarks as bound fermions of fixed number. The residual consists of everything else, the gluons, the C quarks, the meson clouds, etc. And we look at so in this model, the nucleon comes in, decays into a valence residual system, and the valence system decays into 3 valence quarks. So what follows, we're going to just look at this simple, what we're calling soft process here on the screen. And we're going to ignore these higher order ones where there's a 1 gluon or possibly 2 gluon exchange going on. And we'll see how much we can describe with just this soft component. So if we look at the valence PDF, we can express it in terms of the light front wave functions, and we get an 8-dimensional phase space integral. So to model the light front wave functions, we're going to take for the valence component, we're going to look at 3 mutually coupled relativistic light front harmonic oscillators. And for the valence residual, we'll just treat it as the same, except pairwise between the valence and the residual component. So if we assume massless valence quarks, this 8-dimensional integral there can simplify to through a lot of math through this 1-dimensional integral expression, which consists of 3 parameters: this normalization parameter, this parameter here, BR, which shows the strength between the valence residual coupling and the mass of the residual system. So this function peaks. We can get an analytical expression for the peak in terms of the mass ratio, and this implies a limit of 1/4 on the peak, on the x peak of the PDF. And we can also look at the asymptotic as x goes to 1, and we get a 1 minus x to the 4th power. So here we can see 2 fits for the down valence and the up valence. The down valence does well, and for the up valence, qualitatively it matches, but it underestimates at higher x. We can also look at the down versus up ratio, which we took for various PDF sets, and it did not vary too much depending on the PDF set. And here we can see our predictions compared to different models. So we can generalize this for n valence quarks and also derive an expression. So outlook, we can now analyze TMDs and GPDs now that we parameterize our model, and we can incorporate the 2 quark and 3 quark correlations. Thank you very much. This is done in collaboration with Misak Sargsyan